Okay. Sorry for the late start. Um, don't worry, we won't have a late finish either. Um, okay, now um, one thing I want to point out that on the assignments, I don't know how many have started on this one, homework 7. I actually decided to remove a couple of problems. Now, if any of you had gotten started on this and happened to do a problem that I struck from a list, like one of the ones I removed was number 5 in 9.3 is gone. And I think one of the problems in 9.4 I also removed. If you happen to already do them, then go ahead and turn it anyway, and I'll give you bonus points. So that your work is not for nothing. So I also did a little trimming in later assignments. So hopefully that'll be a little more humane. And these are the due dates here that will go by. I've been going through as we go and changing the due dates in Canvas for quizzes, but I haven't always kept up with that. So for any part of the assignment, the explorations or the Canvas quizzes, these are the due dates to pay attention to. Of course, effectively those have become advisory because handling late penalties involves bookkeeping. So, but I figure that if someone is going to subject themselves to doing a whole lot of work toward the end of a semester and dumping it all the last minute, while you have the stress of finals, I think you've been punished enough. So, okay. Of course, I'm also punished too from having to grade it, but still. I'm used to that. Now, okay. Next Thursday, so that'll be November 14th. I'll be down to coast again. Okay. Let's make this a little bigger. All right. So this section is about taking methods that we've already seen for numerical differentiation and integration, and being able to obtain a more accurate approximation from the ones that we're able to compute already. And that's the idea behind Richardson extrapolation, also known as just extrapolation to the limit. So the idea is both numerical differentiation and integration, and I want to emphasize here with composite quadrature rules, produce an approximation that depends on some spacing h. So we're trying to approximate a derivative at a point x0, and we're using values of f at x0 plus h, x0 minus h, etc. When you're using a composite integration rule, like the composite trapezoidal rule, for instance, you're dividing your interval AB into subintervals of width h. So in both cases, the spacing h plays a role. And the error, that's the important thing, the main thing, the error depends on h. Like these approximations are order h squared or h to the fourth. And the idea is to exploit that for greater accuracy. So, how does it get, okay. So extrapolation to the limit exploits our knowledge of the form of the error to produce a more accurate approximation. Literally cancels out the error. Although I think some Math 101 instructors in this room might not approve of that terminology. Okay. So what I'll do is I'll illustrate the standard difference for f prime at x naught. So what do we know about the error in this case? So what we have is f prime at x naught is equal to f x naught plus h minus f of x naught minus h over 2h. And the error is equal to some constant. I'll call it k1 times h squared. And I'll say more about the constant in a little bit, but now, how do we come up with the error formula anyway? Like, how do we show that this expression here is equal to f prime of x naught plus something that's order h squared? How can we do that? Yeah, Taylor expansion. So you would Taylor expand f of x naught plus h and f of x naught minus h, and you simplify as much as you can. Things cancel, and the first thing that doesn't cancel is f prime of x naught, which is what you're after. The next thing that doesn't cancel has some constant unknown times h squared. Now, what happens with these Taylor expansions is, because you're subtracting them, any terms that have a even power of h in the Taylor expansion are going to cancel. Because those terms will be exactly the same in both expansions. So the terms that have odd power of h will survive, but then you divide by 2h, and you're left with items that have an even power of h. So you have f prime of x naught that doesn't have h at all. You have something times h squared, and then the next term will be some other constant times h to the fourth. So the idea there is, and this is something you're actually asked to explicitly show in one of the homework problems. So I've accidentally given you a blueprint for that, if you're paying attention anyway, is to show that the error in the center difference approximation has this form, and this would continue with more even powers of h. Okay. Now, what are those constants? What do we know about them? So k1, and this comes from a Taylor expansion, is equal to, okay, so f triple prime at some unknown point, okay, and then we have over 6. Okay. And then K2, actually I'm going to name the unknown point C1, and then K2 we have a similar form, but that's of a higher order derivative, also to unknown point, and 5 factorial, but also this factor of, well, okay, all right, over 120, and so on, where at each unknown point is between x naught minus h and x naught plus h. So it lies within this interval, but our assumption is that h is small, if we want any accuracy at all. So essentially, we can almost take these unknown points to be roughly x naught. So the nice thing is that we have a really good idea as to what these constants are. Okay. Now, what I'm going to do is show you what can be done if we use this center difference approximation with multiple approximations. Okay. So I'm going to pick out a specific function here. Okay. And I've shown you this function before. This is a nasty one. Okay. One that you would not want to take a derivative of by hand. Okay. Because it would be a nasty application of the quotient rule. This is something I made up just to be obnoxious. Okay. And I'll pick a specific point, x naught equals 0.25. Okay. So we use the center difference with these values, h equals 0.01, and also 0.005. So two h values, one of them is half of the other. Okay. Now, so I'm only going to report the errors, because that's all we really care about. How accurate are these approximations? Because I can go ahead and compute this using whatever software, like by computing a derivative symbolically and plugging in 0.25 to see what I'm supposed to get. So the error with h equals 0.01, and this is the absolute error. So it's 0.003. Okay. And with h equals 0.005, error equals 0.0008. Okay, well, 77. Now, this rule, the center difference, the error is order h squared, second order accurate. So if we cut h by a factor of 2, the error ought to be reduced by a factor of roughly 4. And that's, again, roughly what happens in this case. So, because 0.003 divided by 4 would be 0.00075. So it's almost there. Okay. Now, okay. So I can show you what we could do with these approximations to improve the accuracy with very little effort. Okay. Okay. So I'm going to let di of h be, oh wait, actually not di, just d1. The approximation of f prime x naught computed using spacing h. So in other words, this first approximation is d1 of h. The second approximation is d1 of h over 2. So I'm going to write out what the error would be. Well, first, more notation. Also, I'm going to let d1 of 0 be the exact value. Now, we can't use a spacing of h of 0, because we'd be dividing by 0. But what is a derivative? A derivative would be the limit of this as h goes to 0. So we're going to use this to refer to the exact value. Okay, so then we have the following. So d1 of h is equal to the exact value. Okay. Let me check my... Okay, unfortunately my notation's a little off from before. Okay. That's fine, I'll work with it. Minus k1 h squared. Wait. H squared. And then I don't care about anything after that. So I'm just going to call that something that's order h to the fourth. Okay. Then I do it again of h over 2. And that will also be the exact value. And then I have the same constant. Now, it's not literally the same constant because third derivative is evaluated at an unknown point. These unknown points would be different. But we all know they're clustered around x0. So, although it's not exact to say that it's the same constant, they will be close to one another. And the smaller h is, closer they'll be. So that would be h over 2 squared plus something that's order h to the fourth. Okay. Now, here's what I can do. On the next line, I'm going to take this entire second equation, because h over 2 squared, that would be the same as h squared over 4. So now, whoops, that's h squared, not h to the fourth. Okay. Not sure how that plus got a superscript. Okay. Alright. So now I'm going to take this second equation here, and I'm going to multiply it by 4. So that would be 4 d1 of 0 minus, and if I multiply this by 4, that'll cancel with this 4 down below. So I'm going to get k1 h squared again. And then what's left is still order h to the fourth. Now, something's order h to the fourth, that's going to be pretty dang small. So I'm just going to neglect it. So now what I can do is I can take this equation and this equation and do what with them? Yeah, because if I subtract them, what will that do? Yeah, cancels out the leading term of the error. So, so what I'll get is, well, actually, okay, something went wrong here. Okay. Really, what I'll do is I'll take the second equation, subtract the first one from it. So then I'll have 4d1 of h over 2 minus d1 of h is equal to this minus this, so that's going to be 3 d1 of 0 plus something's order h to the fourth. So now I can rearrange and solve for the exact value. So that's going to be, okay, so this expression over 3. And then what's left is order h to the fourth. So this is how extrapolation works. I take two approximations and I scale them in such a way that the error cancels out. And then, so then I had to use the right scaling factor to solve for the exact value. And what's left will be the same order as whatever is the next term in the error is. Okay. Now, how does this work in general? If we're given the following, so an approximation that depends on some spacing h is equal to the exact value, which is when h is 0, plus a constant times h to the p. And then we do the same thing with h divided by some factor q. All right, so in this example, p and q are both equal to 2. So I can then do the following, that my exact value, okay, and actually I'm going to add on whatever the next term in the error is, so h to the r, where r is strictly greater than p. So in other words, this term ch to the p is the leading term in the error, and then we have lower order terms, higher powers of h after that. So if I repeat this kind of procedure, then what I will get, okay, so carrying out similar algebra, okay, so I'm going to get, okay, q to the pth power times f of h over q minus f of h all over q to the p minus 1. Okay. So that's how it works in general. If you have two approximations, one with spacing h and h divided by some factor, and you know that the error is of a certain order p, so you have to know the form of the error before you begin, then this is how you combine the approximations to get a new approximation that is order h to the r, where r is the next term that's known to be in the error. So any questions about the manipulations that were done there? Yeah.
Shouldn't that be h to the r instead of h?
Oh, yeah, this should be r. Okay. Whoops. Okay. All right. Now, returning to the example that I had, okay, so my first approximation, d1 of h, and I'll recall the error is 0.003, and then d1 of h over 2, error is 0.00077. Okay. We extrapolate to obtain a new approximation, which I'll call d2 of h over 2. So it proceeds using this formula here. So d2 of h over 2 is equal to 4 d1 of h over 2. The more accurate approximation goes first, minus the less accurate approximation. And then now I'm going to actually write it out this way. 2 squared. Okay. And then 2 minus 1. Okay. And the reason why I'm writing out this way is the exponent 2, that's the order of accuracy. The 2 that's the base is what we're cutting h by a factor of 2. And this will become clear as I do more extrapolations. Okay. And what is the error in this approximation? So it turns out to be, let's see, where do I have that written down? Oh, sorry, it should be d2 of h, not h over 2. Okay. I thought I had the error written down here somewhere. Nope, I don't have it here. I have the error for every single other approximation I do in this example except this one. Okay, not to worry, I will find it really quick. Okay, so the exact value that I have down here to so many decimal places. Okay. Don't tell me I don't have that either. Oh, I do. Okay. So I need to make this a bigger font. Okay. So the exact value to several decimal places is 9.066698771242779. Okay. And the approximation for this extrapolation turns out to be minus 9.066701400261449. Okay. So okay, it is a lot more accurate. So the order of 10 to the minus 6 instead of 10 to the minus 4. So, okay, so I'll fill that in. So the error is roughly, I'll round up a bit here, 0.000003. So look how much more accurate it's getting. So here we get fourth order accuracy, second order accuracy, the error decreased by a factor of 4. But now the error is decreasing by a factor of over 100. Because we're going to a whole other plane of accuracy, fourth order accurate. Okay. Now, what I'd like to do is see how far I can take this. So, to go further, we need another center difference approximation. That'd be d1 of h over 4. So in other words, I go back to the original formula, center difference. I've already done it with spacing h over 2. I do it one more time, h over 4. And the error in that approximation is roughly 0.0002. Roughly 1/4 of this. Again, because center difference is second order accurate. Okay. So now, I can take d1 of h over 4 and d1 of h over 2, extrapolate between them, just like I did with these two approximations. Okay, so that would be, I'm going to call that the result, d2 of h over 2. So that would be 2 squared. Okay, I guess I'm on a new page now. So now, this is the less accurate approximation. This is a more accurate one. Okay. So notice the extrapolations have the exact same form. because we're both all cases these are second order accurate approximations, so the scaling constants will be the same. And what is the error? Okay, so that's going to be roughly 0. Okay, so it's 2 times 10 to the minus 7. Whereas here the error was 3 times 10 to the minus 6. What's the ratio? That's 15. The error is decreasing by a factor of 15. Now, I've rounded up here. Really, the ratio is closer to 16. These approximations, d2 of h and d2 of h over 2, because the leading error term is order h squared has already been canceled by the extrapolation, these approximations are fourth order accurate. So the error should decrease, when you cut h by a factor of 2, the error should be reduced by a factor of roughly 16. And that's what happened between here and here. Now, what can I do with these two approximations? I can do it again. So I have to take into account that these are fourth order accurate. So if I go back to my general formula right here, Q is still 2. We're still reducing h by a factor of 2. But P is now 4. So that's going to change my scaling factor. So you have to be careful about that when I go to it. So now, extrapolate from d2 of h and d2 of h over 2 to obtain a 6th order approximation. Because all the error terms in a center difference have even order. So we've already extrapolated to cancel out the second order terms. If we extrapolate between these two, that'll cancel out the fourth order terms. 6th order is what will remain. So what I'll have is d3 of h equals, okay, so now I'll have 2 to the 4th d2 of h over 2 minus d2 of h divided by 2 to the 4th minus 1. So my denominator is now 15 instead of 3. Okay. And the error is going to be pretty small. So that's 2 times 10 to the minus 10. So that worked really well. And the nice thing is, now computing these center differences, that's pretty cheap. And there's the expense of evaluating f of x. That's the main expense there for differentiation. But note that most of the computational effort, in this case evaluating fx, occurs in the original approximations. We're using center difference. Extrapolation itself, almost no computational expense. Yes, there's a little bit, but the thing is, you're not having to evaluate f again. You're just doing a trivial algebraic combination of things you've already computed. So you might as well do it. If you're willing to go through the process of computing this more than once, which is often a good idea anyway, because there's various methods of error estimation and so forth. Mathematical software will often do that just so it can give you an error estimate. You might as well extrapolate from that error estimate to improve your accuracy. Okay. So questions about this example? So the way the way you're producing like a table of approximations, it's kind of like a divided difference table in a way. So if I were to compute a centered difference approximation one more time, like using h over 8, then with all the other information I have, I can immediately do more extrapolations. I can extrapolate between h over 8 and h over 4 to get a fourfold one, and then extrapolate with my other fourfold approximation to get a sixfold one. Then I can go out to eightfolder, and you can do this as many times as you feel like. All right, but again, there's still the expense of the original approximations that you have to take into account. Now, that was for numerical differentiation. We can try the same thing with integration too, because there too you have an approximation that's dependent on some spacing h. The error depends on this h in some way. So again, so you can try using that to get a more accurate approximation. And this leads to a technique that is called Romberg Integration. Okay. So if I were to describe Romberg Integration in as few words as possible, I can easily do so as the form of an equation. So you can think of it as the composite trapezoidal rule plus Richardson extrapolation. So really all you're doing is you're computing several approximations to an integral using a composite trapezoidal rule. First using a certain number of subintervals, and then you keep doubling that. In other words, you're cutting h by a factor of 2 repeatedly. And then you perform Richardson extrapolation among those approximations to increase the order of accuracy. Now, in order to justify this, there's one crucial fact about the composite trapezoidal rule that we need. That the composite trapezoidal rule which I'll repeat here. Okay, so it's h over 2 Okay, so that's the composite trapezoidal rule approximation, where it is evaluating f at many points that have spaced h apart, and then there's the error. Okay, wait, that's 12, not 24. So the error depends on the second derivative at an unknown point in AB, and then h squared over 12. Okay. Now, that is the formula for the error that I derived previously. But we actually know something more about the error than that. And that's what we're going to use. The error is actually a sum of constants times even powers of h. Just like with the centered difference for f prime of x naught. It is possible to describe the error this way. So there's a term of order h squared, this one, plus another term is order h to the 4th, and h to the 6th, h to the 8th, and so forth. Now, where that comes from, unfortunately, there isn't time to go through it here, and actually, the complexity would make you all want to pull your hair out. But if you really want to, it is in this section 7.5. It's called the Euler-Maclaurin expansion. And I'll show you what that looks like really quick because, okay. Okay. All right. This is the actual Euler-Maclaurin expansion right here. So what we have here, well, part of this is exactly what I wrote up before. Integral equals, this is the same thing I just wrote out. That is the composite trapezoidal rule approximation. And everything that follows is another expression for the error. And notice only even powers of h that we have here. And also here. And here, the value k, the number of terms you have, you can take that out as many times as you want, as long as you know that your function f has enough derivatives. So an assumption here is that f has a certain number of derivatives on AB. And if it has 2k derivatives, you can include k terms in this part of the expansion, and then here's the rest of the error here. So there's two important things I want to point out about this expansion. Well, one I already did, the even powers of h, only even powers. So that helps us with extrapolation. I can do what I did with a standard difference, compute a couple approximations of a trapezoidal rule to this integral with h and h over 2, extrapolate between them, and then I know that the error will cancel and give me something that's fourth order accurate. I can extrapolate among those and get sixth order accurate, etc., just like I did with a standard difference. There's one other point that's not really related to extrapolation, but it's well worth making anyway. Right here, square brackets, we have a difference of derivatives of f at the endpoints, a and b. Now, let's suppose, just for concreteness, that the interval AB is, let's say, 0 to 2 pi. And then, suppose my f of x is a 2 pi periodic function. So in other words, your integrand is periodic, and such that the period fits the interval AB. So I could try other periods as well, like pi or pi over 2, something like that, where complete periods fit the interval AB. Now, when you have a function that's periodic, you can actually show that, assuming that derivatives exist, the derivatives are also periodic with the same period. So suppose I take a function that's a combination of sines and cosines, like cosine kx or sine kx, where k is an integer. Those are 2 pi periodic. And of course, you can take as many derivatives as you want. They'll all exist. So what will happen here to these terms? The function's periodic, derivatives are periodic, and here we have derivatives evaluated a and b, which are 0 and 2 pi. What's going to happen to this? It's going to go away. All of this will go away. Now, k is tied to the number of derivatives that exist. But what if all of them exist? Then any of these would go away. So what does that really mean? Learn from this expansion that if f is periodic and a period fits AB, meaning that, wait, I shouldn't have written that here. So what that means is b minus a divided by the period is an integer. Okay. Then the composite trapezoidal rule approximation of the integral exhibits what is called superconvergence. And what that means is convergence that is faster than any power of h. Another way of putting it is that convergence is exponentially fast. So that's one reason why we can never really say that any one integration technique is the best. Certain ones are the best in certain cases. There are certain examples where the composite trapezoidal rule is a terrible idea. That I have to use such a large number of subintervals to gain any accuracy, and I could use something else that would do a better job of less. But when it comes to these periodic integrands, this is the best. None of the other methods that I can tell you about in this chapter will top it. And that's why sometimes in my research I've actually used this, because I know I have that kind of integrand, because it'll give me such an accurate approximation. So these are two key things about the Euler-Maclaurin expansion. A form of the error for a trapezoidal rule, even powers of h, and then when we can expect this kind of superconvergence. Okay. All right. So how does Romberg integration actually work? I can show you the algorithm. Okay. Now, so this is something that could be coded up in MATLAB. First, I want to point out the notation here. I'm computing a bunch of approximations, tj1, tjk. In other words, it's like a matrix. I'm filling out a triangular matrix. Actually, given my notation here, it would be it would be lower triangular. So what's happening here is I decide how many rounds of extrapolation I want to do. That's capital J. Because trapezoidal rule has even order error terms, my approximation will have order 2j when I'm done. Okay. So what I can do here is, this is just a trapezoidal rule with different spacings h. So I choose, first, I only have one subinterval. So h covers the whole interval. So really, the first time around, it's a basic trapezoidal rule. So I'm filling in the first column of my table. So notice the 1 here is the index, as a second index, with just trapezoidal rule approximations, the spacings h, h over 2, h over 4, however many I want to do. Then, as I get these approximations, I can start performing extrapolation. This is equivalent to the formula that I showed you previously. The only thing that's different is just how I've worked with the fractions. And we still have the same kind of denominator here. We still have a difference of approximations. But this right here is the extrapolation. And recall the denominators before. I had a denominator of 4 minus 1 and then 16 minus 1 when I did a derivative example. Same thing here. It's always a power of 4 minus 1. That's because, again, the even order error terms. So as I go to column K, I'm producing, as K increases, I'm producing higher order accurate approximations. That's why the denominator has to be an increasing power of 4. So this will fill in a Romberg table, if you will, of approximations. And I want to see if I actually have that. Well, I can't show you the code because it's one of the problems I assigned. But I can use it. Okay. See if, well, okay, I have it in a bunch of places, but some of these are turned in by students, so I can't necessarily trust them. Okay. Okay, this will work. So I'm going to make a function. Well, actually, all right, notice the, come on, for parameters to this function. First one is your integrand, f. So that'd be like a MATLAB function handle. Then you specify your interval of integration, AB. K is the number of rounds of extrapolation you want to perform. Now, what I will do is I'm going to call this function. I'll just use the exponential on the interval 0 to 1. And I'll do 3 rounds of really it's 2 rounds of extrapolation, but 3 columns of data altogether. I want to see what it prints out. Okay, well, it just gives the approximation. And the exact is the integral of e to the x from 0 to 1 is e to the x with limits 0 and 1. So this is the exact value. Okay, so it's pretty accurate. At least, okay.
Would it be a difference if you formatted it wrong?
Yes, it would. All right, so so the error is the exact minus the approximation. Okay, so it's pretty accurate. But it isn't what I wanted to show you. Now I have to be careful here because okay. If I disconnect this, the recording will stop. Okay. See, do I want to do that? Okay. So I can do the following. Specify additional outputs. R will be my Romberg table. It'll show me all the approximations that are computed. E will give you, actually, I don't want that. Well, I'll see what it does anyway. Okay. Okay. Let me make this a little bigger. Okay, this is what a Romberg table looks like. So first column computed just using the composite trapezoidal rule. Here we use 1 subinterval, then 2, then 4. So that keeps doubling. Now the exact value is 1.718 something. So it is getting closer, but only second order accurate. Then I take these two values and extrapolate from them to get this one. So the second column, those are approximations that are fourth order accurate, and they come from extrapolating from values to its left. This one comes from these two values. So you're always referring to the value to its left and then the one above it to do the extrapolation. And then, finally, I take these two and extrapolate between them to get this one. These are fourth order accurate, so my denominator is going to be 15 now. And this one is sixth order accurate, and it's certainly a lot closer. Now, I'm going to show you the errors now. Okay. Well, yeah, the errors, that's weird. Yeah, the errors only cover the last two columns. So that's disappointing. But, actually, oh, I see what it was doing. All right. I'm going to forget about this. I'm going to compute the error a different way. Because we have the exact value already. So if I do absolute value of the approximations minus the exact, but I don't want to affect these zero entries up here, so I'll just take a lower triangular part. So this will show me the errors. I think this was done just using some estimate, which isn't really reliable. Okay. Yeah, this is what I'm looking for. Here are the errors in all my approximations. Notice in this first column, the error decreases by a factor of about 4, which is what we'd expect for second order accurate. Then over here, here it's decreasing by a factor of roughly 16, which is what you expect for fourth order accurate. And then this approximation is sixth order accurate. We don't have another one to compare it to, but notice it's much more accurate than what we saw before. So this worked quite well in this case. So you just do composite trapezoidal rule here, and then extrapolate this and these top two to this one, the bottom two to this one, and then these two over here. Now here I only extrapolated out to sixth order. I could have gone further. Like if I do 4 rounds, then these top 6 values were not top 9 entries were all the same, but I kept going. So here, notice the errors decreasing by even at an even greater rate. The ratio should be about 64, which is 2 to the 6. And look how accurate this is. But there's one thing I want to point out is it doesn't always work this well. And this is the focus of one of the homework problems. So I'm going to show you an example where it doesn't work as well. All right, so I'm going to do the integral of square root of x. Now, the integral of the square root of x from 0 to 1, the exact value is 2/3. Okay, so now I do, instead of exponential, I do a square root. Now let's go out to 6th order. And knowing that we're supposed to converge to 2/3, well, yes, it is kind of getting closer to 2/3, but it's not doing a good job of it. Let's look at the error now. That's pretty awful. We're not even getting second order accuracy here. Here, it's not even second order accuracy here. It's so the error is decreasing by a factor of not even 3. So it really bombed out in that case. Now I'm going to do one more example. Same function, but I'm going to go from 1 to 2 instead of 0 to 1. So in that case, the exact value is going to be, so 2/3 x to the 3/2, so it's going to be 2/3 times 2 to the 3/2 minus 1. Okay, so this is the integral of square root of x from 1 to 2. Okay. All right, and if we look at the approximations, well, that's working really well again. Look at the errors. Not as dramatic as the exponential function, but we are getting second order accurate here. We are getting fourth order here. So what gives? Well, that's the homework problem. So by examining the error term, the error formula for a composite trapezoidal rule, you can get an idea as to why this behavior happened. So it's not so much the extrapolation that bombed, it's really the trapezoidal rule that bombed. Because it failed to live up to its second order accuracy. The error ended up not having a form that we expected. And that's why so that's why this happened. So one thing to keep in mind is there's a big difference between using Richardson extrapolation for derivatives as opposed to integrals in terms of effectiveness. Because if you look at the error in both formulas, so here's the error, the leading error terms for derivatives. We have an unknown point plugged into the third derivative, but where's that unknown point? It's contained in a nice small interval. Whereas for the trapezoidal rule for integration, here's the error. Again, an unknown point plugged into the second derivative. Where's that unknown point? Anywhere in AB, not a small interval. So right away, that tells you there's some inherent risk in using extrapolation with integrals as opposed to derivatives. Okay. Now, but just to give a clear example as to how Romberg integration proceeds, because I remember when I took this class way back in 1988, one of the problems in the final exam was to carry out Romberg integration by hand and calculator. So it can be done. All right. Well, I'm going to show you how it goes. It's not like I'll ask you to go to 10th order or anything. Okay. So the integral in question is a Gaussian function, e to the minus x squared dx. Okay. So here are the approximations that are computed. Okay. In the order which we can compute them. So first, approximation is trapezoidal rule with only one subinterval. So, so that would be 1/2 f of 0 plus f of 1. Okay. So, and the error, okay. See, do I have that here? Yes, I do. Okay. 0.0063. Okay. All right. So we're just using the basic trapezoidal rule. Your integrand evaluated at the endpoints times b minus a over 2. So that's really where this 1/2 comes from. So in fact, I'll just make that more explicit. Yeah. b minus a over 2. Okay. Then, we can't do an extrapolation yet. We need a second approximation with a trapezoidal rule. So, all right. All right, so our initial spacing is h. That'd be 1, the whole interval. Now we cut that in half. So Now, the trapezoidal rule always has h over 2 out front. So now we're going to have 1/4, and it'll be f of 0 plus 2f of, plus 2f of 1/2 plus f of 1. So that's a trapezoidal rule, composite trapezoidal rule on 2 subintervals. Okay. So that's where this sum first comes into play. Whoops. Okay, and the error in this case just turns out to be 0.015, so roughly a quarter of this. Okay. Now we can extrapolate between these two. So that would give me, all right, so the more accurate approximation plus the difference of the two, again, it's a more accurate minus the less accurate. And because it's second order, it's over 3. Okay. So the error in this case is going to be 0.0036. So again, roughly 1/4 of this. Well, actually, no, I can't comment on error because this is 4th order. I don't have anything to compare to yet. Okay. Now, to do any, now if I was only if my value of capital J, the number of passes, was equal to 2, I'd stop here. But if I want to go any further, I need yet another trapezoidal rule approximation. So I'll call it T31. Remember, first column is just trapezoidal rule. So that would be where'd it go? No, really, where'd it go? Okay. All right. So that would be 1/8. So whatever's out front, just cut it in half. So f of 0 plus 2 f of 1/4. So remember, your spacing is always getting cut in half. F of 1/2 plus 2 f of 3/4 plus f of 1. So the error in this case turns out to be, okay, 0.0038. Okay, whoops. It's something seems off here. Oh, yeah. All my trapezoidal rule approximations are off because apparently I can't read scientific notation anymore. Okay, all right. And yeah, and this is roughly 1/4 of this. Okay. Now I can take 2,1 and 3,1 and extrapolate between them. Stop it. Okay, so that would give me T32. So that'd be T31. Notice the index patterns here. Whoops. I hate when I do fractions in LaTeX. It always just makes things completely disappear. Okay. So here in your table, you take the one to the left and a one above it. And that's what you extrapolate from. So the error in this case, in 3.2, is, okay, so if we compare the previous extrapolation, so it's a much higher ratio of errors because it's 4th order accurate now. Okay. And then finally, I could take T32 and 2.2 and extrapolate among them. It gives me T33. You're always going to stop on a value where the row and column indices are the same. So that would be T32 plus T. Dang it. Stop it. T22. And now, because I'm extrapolating among fourth order approximations, my denominator will now be 15. Okay. So the error in this case is going to be 0.01. So it's going to be more accurate still than the previous ones, because this is a 6th order accurate approximation now. And I could go further, but that's but here's how we get out to the 6th order at least. If I wanted to go out to 8th order, I would need one more trapezoidal rule approximation to be called T41. And I have 1/16th, and I'd be evaluating f at every 8th. And then I could do 3 extrapolations from there. So questions about how this was carried out?
Where did you get 15 for T3?
So if we look at the algorithm, it's always a power of 4 minus 1. Yeah. So 3, 15, 63, etc. And that's because of the even order error terms. Other questions? Okay. All right. Let's see. Now, one thing I want to point out, we take a look at where f was actually evaluated. We have first time through 0 and 1. Second time through 0 and 1 again, and then 1/2 is new. Then down here, 0, 1/2, and 1 repeated. 1/4 and 3/4 are new. So if I were to go again with spacing of 1/8, all of these function values would be used again. And I have new ones to fill in. 1/8, 3/8, 5/8, 7/8. So that's what happens every single time you go from one level to the next. Roughly half the function values you need in your trapezoidal rule approximation have already been computed. And then you have the other half that you have to compute new. And that is not accounted for here. If you do this exactly as written, it's going to be wasteful. It's going to compute those again. But I do have it worked out here. Okay. How you would do this more efficiently. All you have to do, so what's done here is this is your trapezoidal rule approximation, but the sum in the middle is separated between odd numbered points and even numbered points. So it turns out that a trapezoidal rule on a certain number of subintervals is equal to 1/2 what you get from half that many subintervals, and then these function values added on. So this would be a more practical way to do it that evaluates f only at the points where it's actually needed. So the algorithm could be modified to do just this. Over the course of the algorithm, that would literally save half of a total function evaluations compared to what's written in there now. Okay. Because remember, with integration, the efficiency is measured by number of function evaluations, because those might be expensive, especially for some of these crazy functions I've concocted. And really, you never know how expensive it's going to be. So it's important to keep that to a minimum. Okay. In the last minutes, okay. Sorry, this monitor's off here. It's throwing me off. Are there any homework questions of any kind? Is anybody doing any homework? Every now and then I look through my folders, because I every time I get a new assignment submitted, I have folders set aside for homework 1, 2, 3, 4. And then I look at them now and then, and once they reach like a critical mass, then I go through and grade them. and it hasn't happened lately. So get them in. We're running out of semester. Yes.
What kind of answer are you looking for 7.5.2?
752.
Something in the run form?
Okay. Oh, okay. The answer I'm looking for is a particular type of polynomial. So in other words, there's an actual name for it. I think you threw out Lagrange. It's not that, but it's that kind of answer, yes.
So it's like a
Wait, what? Okay.
It's a very familiar one.
I'm sorry, my
Very
ears are...
familiar.
What?
Very familiar one.
Yes. Yeah. One everybody here should definitely have heard of, because it plays a key role in a prerequisite class for this one. What I would suggest for that one is if you work out an example, let's say n equal 2 or 3. Write out the divided difference table. So you'd have all f of x naught, that first column. And then the later columns would be filled with the appropriate expressions, which is described up above. And then, what do you do when you complete the divided difference table? You form the Newton polynomial. Write out what that is for an example, and you'll see. Other homework questions? Okay, fine. I want to get out of here too. Well, we finished integration on Thursday.